Welcome. Uh, Today I will show you how to carry out internal flow simulations with Ampersand. But first, I have to guide you through a little bit of some workarounds especially for internal flow problems. And one of the most important thing is to import the largest STL first. So it's the largest wall. For example, if you are simulating a pipe, it's the geometry of the wall, pipe wall first. If you first input, for example, patches for inlets or outlets, the Ampersand will have problems correctly computing the background domain for the simulation. Okay, so that's the first one. And the second one is, if your geometry is symmetric, you may be able to use a half simulation. So if your pipe is symmetric, for example, you may be able to use. But if it isn't symmetric, please do not use the half simulation model. It will cause problems. And the third one is, you may need to visualize the geometry first to properly set the velocities for inlet pitches. Currently, Ampersand does not provide the normal velocity boundary conditions, but I'm working on it. So in later versions, this problem will be gone. So let's get started, and I will turn on the Ampersand. Before starting Ampersand, I will show you the geometry to use as a reference. So it's the exhaust geometry, and here we have these. Okay, so this is the geometry for these. And okay, let's cool. So this is the geometry. We have 4 inlets and an outlet. This one is I explained in the last Salome tutorial. So I extracted the fluid domain from the surface geometry and made it as an SDL. So I will be using this geometry, and before I will show you the direction of the inlets. So the inlets are in, as you can see, in the positive z direction. So we have to keep it in mind, and otherwise the inlet direction will be wrong. Okay, so I have the idea of the geometry and the inlet directions look like. So turn on the Ampersand python main.py and create first. And Ampersand will start, and it will ask you which project directory I want. So it's Ampersand tests. So this is the directory to keep your project directory. This is not the project directory yet, so select the folder and give a project name. I have a manifold. Okay, I'll give it exhaust manifold. So the first setting is to choose whether I want to use a coarse mesh, medium. A good recommendation is to always start with the coarse, and it will give you an impression of how things will look like. And if you are not satisfied, you can go to medium, or you can use Ampersand's open mode to change the settings. Okay, so and then the the first thing you have to do is choose SDL. Yes, and I have to use these patches, wall first. So this is the largest SDL in the group. So, and give it a purpose as wall. Okay, and then I will go with inlets. After the first, the order does not matter, so I first go with inlet 1, and the purpose number is inlet, so I use 2, and velocity, so it should be velocity in positive z direction, 0, 0, 0.5. So this is x, y, z directions. Another STL, yes. So to show you the that I don't need the ordering anymore, I will add the outlet. 3, it's outlet. Okay, and I already added inlet 1, so it's inlet 2. Okay, and 2 is inlet, and 0, 0, 0.3. Yes, inlet 3, and 2 is inlet. Velocity vector 0, 0, 0.4. Okay, yes, inlet 4, 2, inlet 0.6. Okay, so I have imported all the STL files. I don't need to add another STL anymore, so no. Internal or external flow, this is very important. So since we are doing internal flow, I will choose the I, which is internal flow. Okay, so and after that we have to choose the fluid properties and inlet values. The fluid properties, if you input 0, you can choose the properties manually, namely the density and the kinematic viscosity of the fluid. And for now I will set air, so choose 1, and setting inlet values, the transient or steady state, I will start with steady state. Okay, S, number of cores, 4 cores. Okay, half model, so this is not symmetric geometry, so I will have to say no, and it will set the mesh settings and y plus values. And you want to use the function objects. Yes, I want to see the flow variables, so now it computed everything and generated the case files. So we have these walls, inlet 1, outlets, inlet 2, 3, 4, and we have this purpose, and the purpose is walls, inlets, outlets, etc. And for the inputs, inlets, you can see in the property we have these values, which are velocities. So the properties is just a universal value. If you have special values, you will see this here. Okay, so the created boundary conditions and boundary conditions files, so everything seems fine. Okay, so I will go to the directory in my Docker Linux environment, cd exhaust manifold, and I will have true, just ls is fine. And I have these settings files and run scripts, so I will start run the mesh. You have to start running the mesh, it will generate the mesh, and it will create a coarse mesh, and we can see the results in exhaust manifold, this one. So this is our guy, and snappy hex mesh is still running. Oh, it's already done. Okay, and I will check mesh. So the mesh is fine with only 40,000 cells and with non-orthogonality 60 and skewness 2.5. So it's quite a good mesh in terms of matrices. So I will visualize the mesh. So these, I don't need these anymore. Oops. And source manifold, this guy. So this is quite a coarse mesh, of course, but you can see here we have one layer of one boundary layer here, and the mesh is okay, especially for a coarse mesh with 40,000 cells. Okay, so I will try to run. It will run renumber mesh and simple form, and you can see the log file here, log.simple form. Okay, now it's running, and so the residuals are dropping real fast. Oh, it's already done, so it seems converged, maybe. So I will check the convergence by visualizing the results. So what I should do is I will use this post mode. Now the ampersand has 3 modes: create, open, and post. So I will run the post mode by running this command, and what I will do is I will choose the case file, exhaust manifold, and select the folder, and it will create the residual plots. So now the residuals dropped really well at the very first, and now omega is a little bit oscillating, so it means the residuals are not going down maybe anymore, and simulation converge very well. So I'll close it, and now the next part is there is a probe point, an arbitrary probe point, which is inside the domain to see whether the solution is converged, the flow field is converging or not. So this is the flow velocities in that point. You can change that by manually, and or you can change inside the open mode. Okay, and this is the pressure. So now it's going very steady. It was oscillating a bit, and now it's steady. And the forces on the wall of our walls, and so this is like the friction force dominates. So the simulation works very well, and we converged, but as you can see, okay, we have to visualize the simulation, and here we have this little contour plots, which seems fine, and you can also see the y plus values. So how much? Wow, this is too low. The y plus is too low, so that's why I think the residuals omega has start oscillating. I forgot to say these post-processing files, the monitoring files, are already here in your directory if you run the post command. Okay, and maybe I can refine the mesh more. So what I will do is go to the open mode. So main.python open. So it will go prompt to select the project directory, and again you will choose your case directory, and it will show the number of cells, maximum cell size, background cell size, and refinement levels, etc. So, and it will ask you to modify the project settings. I say yes, and you can modify as many things. Honestly, I have not implemented about the boundary conditions and simulation control settings, but the rest you can do this. Okay, so I will show you how to change the mesh size. And the first one is the background mesh, by changing the background mesh size. So choose one. So now we have the idea of the background mesh size and the domain size. So I will not touch the background mesh domain size itself. So I will choose the cell size, change the cell size. So change domain size, no, I keep it there. Change cell size, yes. So maybe refine a little bit. So this is around 0.02 meters for the background block mesh. So I will go with 0.01. It will be much smaller. Okay, as you can see, the background mesh size is 28, 15, 11 to it increase, it doubled. And you want to modify another settings? Yes. Okay, and you can change the refinement levels. So I will show you that part 2, and to choose the for add geometry, we cannot add because this is an external flow and there is no point in adding geometry, but it's possible. Okay, so these are refinement levels. I will increase the refinement levels of the walls to maybe 2, 3. Okay, so the number of the file is 1. Okay, I will change. This is the number of about the walls. The refinement minimum is 2, maximum is 3. Okay, so now in this list you can see our walls increase from 2 to 3. Okay, you want to modify another settings? No, I'm done. I think I am fine, and that's it. It will already generate. It's already generated the settings files, new settings files. So I will go back to the case directory and mesh again. So this time it will take a lot longer because I increased the background block mesh size as well as the refinement levels. So at least the mesh count will increase 8 times at least, maybe 10 times. So I will go to the snappy hex mesh. Where is the snappy hex mesh file? Ticked, logged. Okay, here. Okay. It's running. So this is mesh morphing. It will definitely take a lot of time. So now it's adding the layers, and yeah, it's now finishing. So let's see the new mesh. So now this is a much finer mesh, as you can see, but these edges are not fine. Yeah, we have some problems here. Maybe we have to increase the refinement levels of the edges. Okay, but anyway, this is a little bit better. Now we have here these areas. So I will run the simulation again. Run. This time the simulation will take more to finish. So let's see the residuals. We can see the residuals even before the simulation finishes. So Python main.py and post. And now we choose the exhaust manifold. So it's dropping steadily. It's just not converged yet. And yeah, the flow variable seems fine. It's not converging, it's just changing, but it's gradually converging. And you can see the log file from here. Now 88 steps finished. Okay. The default write time is 100 for steady state simulation. So we will see the first simulation. In a few seconds. Okay, so now we can see it, see the results. The pressure, and maybe you can slice somewhere. Or yeah, so and you can see the velocity inside these sector. Now the flow velocities are really stable and pressure stable, forces stable. Has the simulation converged? So now the simulation is converged, and you can see it converged in like 200 steps. The convergence criteria is 10 to the power -4 for velocities, and 10 to the power -3 for pressure. So you can use tighter convergence criteria. So I will show this again. It's a little bit oscillating, but it's still dropping, but the flow variables are not oscillating anymore. So I think this is a good convergence. So this is how you can use Ampersand to model your internal flow problems, and I will add more advanced details and features. So please stay in tune, and thank you for watching. Bye bye. See you.